All right, everyone. I ran into a little bit of a problem with the screencast for some reason from my last lecture, and so I'm redoing it here in my office. I don't know what happened. There was a problem, I guess, with my external microphone. I don't know if it's a problem that I had with it or if something's going wrong with it. But anyway, I'm using the built-in microphone now on the computer, so hopefully everything is being recorded nice and clear here. So this isn't the actual screencast from the lecture, but I'm going to go through it again for you so that you have access to this on the YouTube channel. So if you look at the reaction where you take hydrogen and chlorine gas and you mix them together, you can actually get 2 molecules of hydrochloric acid, or HCl gas. Now this reaction is kind of an interesting reaction in that if you take hydrogen and chlorine and you put them in a tube with 2 open ends, and then you stick corks in the 2 open ends, nothing happens in the dark. But if you tell somebody to walk up and take a picture of it with a flash, when they take the picture, the flash starts this reaction off and you get an explosion, a small explosion, and you generate HCl gas and a lot of heat, and the corks come out the side. A spectacular demonstration, but nonetheless, it's a free radical reaction for the formation. And so if you look at the energetics here, or the enthalpy terms, you can see the bond association enthalpies quite nicely. And when you apply that equation that you learned about in general chemistry, remember sum of the products minus the sum of the reactants gives you the delta H of the reaction. And we plug all these numbers in. What we actually see is that this reaction is exothermic by 185 kilojoules per mole. So it's a fairly exothermic reaction, and that accounts for the small explosion that would happen in the tube that I just described to you. Okay, and so remember, it's bonds gains and bonds lost, and overall, if that number is negative, you get an exothermic reaction. So that explains why it's always products minus reactants, because in the products you're gaining bonds, and the reactants you're breaking bonds, and so that's why you set that reaction, or excuse me, that equation up the way that you do. Now, if we look at this reaction, we look at the enthalpy on one axis and the reaction coordinate on the other, we can see that hydrogen plus chlorine goes to 2HCl, and that energy difference is 185 kilojoules per mole, and it's exothermic. And you can really think of this as chlorine going to 2 chlorine radicals. Those chlorines should say 2Cl dot, a single dot for a single radical, because you're breaking these bonds in a homolytic fashion. And hydrogen can dissociate and give you 2 hydrogen radicals. And so if those combine, you should end up with HCl. However, this isn't how the reaction actually occurs. It's not really 2 hydrogen radicals plus 2 chlorine radicals plus 2 HCl's. The mechanism is a little more complicated than that, and we'll talk a little bit more about that here as well. Okay, so the mechanism of this, actually, if you look at the mechanism, the concentration of radicals at any given moment is essentially 0. There's really not much in terms of a concentration of radicals, because once we generate a radical, it's a highly reactive species, as they don't have an octet, and so they'll react very, very quickly to attain their octet. And so you're not going to have hydrogen and chlorine just spontaneously break down into radicals that then somehow miraculously rearrange or find each other and form HCl. Just doesn't happen that way. These reactions actually are what are called chain reactions, and we'll talk more about the mechanism of those in just a moment. Okay. Now, if we look at carbon-hydrogen bonds, remember early on in the semester we talked about the fact that there are different types of hydrogen. There are primary hydrogens, secondary hydrogens, and tertiary hydrogens. And I mentioned to you at that time that this would come back and be important in Chapter 10, and here we are. And so if we look at propane, you can see that we have 6 primary hydrogens. And if we remove one of those hydrogens in a homolytic fashion, that is to where one electron in the CH bond goes to carbon and one goes to hydrogen, we end up with a primary radical, and that takes 423 kilojoules per mole of energy to break in a homolytic fashion that bond. If we look at the secondary hydrogens of propane, we see that it takes actually less energy to break that CH bond. It only takes 413 kilojoules per mole. Okay, and this has to do with radical stability. So you can see in the first reaction you're generating a primary radical, and in the second reaction you're generating a secondary radical. And it turns out that radical stability mirrors that of carbocation stability, because both a carbocation and a radical are electron deficient species. And so the more substituents you have around a radical, the more stable it should be. And that's exactly what we're seeing here. So primary radicals are less stable than secondary radicals by approximately 10 kilojoules per mole. Okay. Now we can also look at isobutane, which has primary hydrogens and tertiary hydrogens. And so if we look at the tertiary radical, so that is we're going to break the carbon-hydrogen bond to that tertiary carbon, you see that it takes about 400 kilojoules per mole to do that. So again, even less energy than what we saw for the secondary radical at 413 kilojoules per mole. Okay, and again, the primary radical is about what you saw for the other primaries as well. So about 422. I think the other one was 423. And so you can see primary is certainly less stable than secondary, is less stable than tertiary in terms of radicals. Now, radicals and carbocations share a lot of things in common. However, radicals rarely rearrange. I'm not going to say they don't, because there are some examples where radicals do rearrange. But for the purposes of this course, radicals don't rearrange. And whereas we could not generate a primary carbocation, we can readily generate primary radicals. So those are some differences, although the stability kind of trends with one another. If we look at a different type of molecule, let's look at ethylbenzene. Again, we can see some bond association values here. So we can generate a primary radical by removing one of these hydrogen atoms to give us a primary radical. That takes about 410 kilojoules per mole. Notice it's not exactly the same because of the benzene ring. We can also remove one of these secondary hydrogens, and notice here it's very low in energy. It only takes 356 kilojoules per mole. The reason is this isn't a typical secondary radical. This is actually a benzylic radical. It's a radical on a carbon attached to a benzene ring. And the reason that this is so easy to abstract is because this radical is actually in resonance with the aromatic ring. So as an exercise, why don't you stop this screencast and actually draw out all of the resonance structures for this radical. So you'll have to push single barbed arrows from the ring to the radical, and you'll see that you'll get a whole set of resonance structures that explain why this radical is so stable. Also, you'll see here abstraction of a hydrogen from the actual benzene ring is very high in energy. That's not a very stable radical because this actually is not resonance stabilized by the benzene ring. If you look at the hydrogens are actually perpendicular to the plane of the pi orbitals, and so you can't draw resonance structures for this particular radical, whereas you can for the secondary radical we have here. And so the reason that we see this increased stability has to do with hyperconjugation, just like we explained for in carbocations. Remember, the more substituents you had, the more of this hyperconjugation you have, which stabilizes the carbocation. Well, the same thing happens here, except a radical is present as opposed to an empty p orbital with a positive charge. Okay. Now, I want to show you this. This comes from the materials provided by the book author, but this is just absolutely nonsense. Okay, so notice that they're trying to explain to you this hyperconjugation effect by what they say is resonance structures. And so if you look at this carbocation, they're saying that this is a resonance structure of a carbocation, and that is absolute nonsense. Okay. Likewise, they are showing that they're trying to explain that this and this are resonance structures. These, in fact, are not resonance structures because you've actually broken a sigma bond in the process of doing this, and atoms have moved. We cannot move atoms in resonance structures, and so these two things are just X them out. If you see them in the book, just X this stuff out because This is the right explanation here. It's the hyperconjugation of the adjacent alkyl groups with the p orbital that's responsible for the stability, not this so-called resonance business as they have it drawn here. Okay, so just get that out of your mind. Now, radicals are very reactive, and they'll react with a lot of different things. And so for the purposes of these slides, let's just assume that X radical is a halogen atom. So let's say it's chlorine, so it's the chlorine radical. Halogen or chlorine radical will react with hydrocarbons to remove the hydrogen and generate a new carbon-centered radical, as we call it. So you get a molecule of hydrochloric acid in this particular case. These radicals will also react with carbon-carbon pi bonds. As you recall, pi bonds are weak, and see how we have the arrows here. And so we can go from this radical to a new carbon radical. We can also have radicals reacting with one another. So if we have two chlorine radicals that come into close proximity with one another, they will rapidly react to form a Cl2. And so that's why you don't have a whole lot of radicals in solution at any given moment in a radical reaction, because once they get close to one another, they immediately react. So the radical concentration is always low. And radicals will also react with oxygen. The oxygen that we breathe is actually a diradical. If you recall back from your general chemistry where you were looking at the orbital diagram for molecular oxygen, you should recall that there were two orbitals that were told to you as being degenerate. That is, they're of the same energy level, and one electron went into one orbital, and by our filling rules, right, we put the second electron in the next orbital, and then you ran out of electrons. And so you had two orbitals of the same energy level that each had a single oxygen, or excuse me, a single electron on each oxygen atom. And so that's why the air that we breathe is called triplet oxygen, because there are actually two single electrons that are on each oxygen atom. You might be wondering, why don't you just have these two radicals react with each other and have an oxygen-oxygen double bond? Well, it comes out of molecular orbital theory, like I just mentioned. You can do that through a trick, and it's called generating singlet oxygen, which is highly reactive and very, very toxic. So it's fortunate for us that oxygen actually is a diradical species. We can halogenate alkanes very, very easily and make alkyl halides. If you think about the ways in which we've made alkyl halides thus far, we've made alkyl halides by reacting HX with an alkene, following Markovnikov's rule to give out alkyl halides. We've reacted alcohols with strong acids, like HCl or HBr, to give us alkyl halides with the loss of water. But you can also halogenate hydrocarbons quite easily. So for example, if we took methane, chlorine gas, shine a bright light on it or heat it up, you can actually make methyl chloride very, very easily, plus you get a molecule of HCl. You can do the same thing with brominations, and you can get alkyl bromides plus HBr. You can also react halogens with molecules that have more than one type of hydrogen. So like here's our propane where we have primary and secondary. And what you get, as you might expect, is a mixture of products. And what you should notice is kind of odd is that you get a 1-to-1 ratio of these two products, when in fact you might predict that the primary alkyl halides, you should have gotten 3 times as much of that, because you have 3 times as much primary hydrogen as you do secondary hydrogen. And so that tells us something about the reactivity of these different hydrogens. Okay, so secondary are clearly more reactive because we're getting more than expected secondary alkyl halide product from that particular reaction. Now it turns out that on a laboratory scale, the halogenation of alkanes is actually fairly useless, especially for chlorination. So for example, if you came into the laboratory and you took a test tube full of methane and you put some chlorine in it and you shined a bright light on it, you would actually end up getting a whole mixture of products. First off, you'd get a lot of HCl gas coming out of the reaction, but also you'd get methyl chloride, which would then continue to react to make dichloromethane, which would then continue to react to make chloroform, which would then continue to react to make carbon tetrachloride. And so you'd end up with a distribution of all four of these products plus the HCl. And that's not very practical on a laboratory basis. However, this is practical on an industrial basis because all of these products can actually be packaged and sold as commodities. Chloromethane is a useful molecule that has a market. HCl, of course, as hydrochloric acid. Dichloromethane, you've used that in the laboratory. Chloroform is a very useful organic solvent as well, and carbon tetrachloride used to be used quite a bit for a variety of purposes, especially in the dry cleaning industry, although it no longer is because it's highly carcinogenic. But nonetheless, you can generate all these products on an industrial level, package them up separately, sell them, and make a profit. Now, there are some things that you need to know about the halogenation of alkanes that allow us to know that the mechanism must involve a radical. And so here on the left we have some facts, and it turns out that light heat or added peroxide is necessary for this reaction to go. That is indicative of a radical reaction. And so by light, I'm not talking about just like the light here in the room, but I'm talking about the light that you might get from like a sun lamp. And heat, I'm talking about a lot of heat. We know that oxygen inhibits the reaction because oxygen will react with the free radicals, as we mentioned in a previous slide. And we also know this because we don't see rearrangements. And we know that radicals don't readily rearrange. So all of these facts tell us that the mechanism for the halogenation of alkanes involves a radical and not some type of ionic intermediate. That is, it doesn't go through an SN1 or an SN2 type reaction mechanism. Okay? So I'm going to just have you look at the halogenation energetics. This is just the stuff that you learned about in general chemistry, looking at the bond dissociation enthalpies. You can see overall that the halogenation of ethane with chlorine gas is an overall exothermic by about 28 kilocalories per mole. But the mechanism involves three steps. All free radical reactions have three steps. They have an initiation step, they have propagation steps, and they have termination steps. And you can identify the initiation because you have no radicals on the left and you generate radicals on the right. And if you go back and look in your bond dissociation enthalpy list of energies or enthalpies, you'll see that the chlorine-chlorine bond is actually fairly weak. And so when you take ethane and chlorine and you shine a bright light on it, the first step is the generation of radicals, and those radicals are chlorine radicals. Those generated chlorine radicals, then being highly reactive, will react with the ethane that is present and abstract a hydrogen atom, as shown here. That then generates one molecule of HCl as a product, but it also generates a carbon-centered radical, which in and of itself is very reactive. And so that radical then reacts with the chlorine gas that's present, and you generate the product, chloroethane, plus you generate another chlorine radical, which then enters back into the top propagation step, and this continues on and on and on until we run out of reagents to react with. Now, how do I know that these are propagations? I know these are propagations because I have radicals on the left and the right. Now, they are different radicals. You go from a chlorine radical to a carbon radical, but nonetheless, there are radicals on the left and the right. You can have, in theory, an infinite number of propagation steps. For those of you who are in polymer science, if you've ever talked about free radical polymerization, you'll know that you have multiple, many propagation steps that lead to the final polymer product. Once the concentration of my reactants gets really, really low, the concentration of my radicals all of a sudden spike up and they start to react with each other in a process called termination. Now, there are several different types of termination steps, as you can imagine. 2 chlorine radicals coming together, 2 carbon radicals coming together, or a carbon radical and a chlorine radical coming together. But in all cases, you see that you have radicals on the left and no radicals on the right. That is indicative of a termination reaction. So I'm going to let you look at these problems. These problems come from the ACS standardized exam study guide. and I'll let you determine how we come up with these answers on your own. We did these in class, so feel free to pause at any moment and work your way through it before you see the answer. Now let's take a look at where we got on the last part of the chapter. Now, we started talking about the fact that we can have initiation and we can have propagation, right? And we can have termination steps in these reactions. And there are many different types of terminations that you can imagine, and for this particular reaction, here are the three that you have to pay attention to. And I think that's about where we got. We'll finish up with this in class on Monday and have our inverted lecture.